Now we're on the same page. So let's start again. All right, so Michael Johnson.
This race is brought to you by Visa, the official card of the NFL, and the only card accepted at the Olympic Games. And the Visa Triple Crown. Almost forgot. We're also the official card of NASCAR. Visa, it's everywhere you want to be.
It's a cute little commercial. They're just making fun of the fact that they couldn't figure out who the fastest person alive was. This is like 15 years ago. All right, so what's motion? It's a displacement of mass in time and in space. All right, once again, guys, everything that you see in red needs to be expressed in the way we measure them. All right, so having said that, let's talk about mass. The easiest, we're going to talk about mass, time, and space. Let's start off with the easiest one. The easiest one is time. All right, so let me ask you this question. What is time? Okay, so we will have this weird discussion regarding time. Is time a human invention, or is that something that we get from nature itself? What do you guys think?
It's natural. Nature.
Okay, so those of you guys who said it's something that we get from nature itself and natural, give yourselves 2 points. Just justify that. What makes you think that it's natural?
Well, regardless of whether or not we were here, time would still be present. We may have given it a term and defined it, but it exists without us.
Okay, so you're making the point that the time exists whether or not we're here. So how do we know that the time exists independent of us?
You see the change, as for example, like the trees. You know, there's a time where you see the leaves, you know, they're growing, and then they die and they fall, and you see the same cycle over and over. So there's something going on.
Okay, Efren, I'm gonna give you 5 points for that one. Okay, so time is natural, so we get time from nature itself. But how do we know that the time passes, aside from the fact that the tree gets bigger, kitten turns into a cat, and that sort of stuff? All right, so you know that the time passes, right? How do we know that? Because the time is cyclical. We go around the sun, it takes a year. And within that 1 year, what happens? We end up experiencing 4 seasons because we live in Chicago. And that's it. So that we call that a single year. So you can break it into, obviously, 4 seasons, 12 months, months into days, days into hours, hours into minutes and seconds, and so forth, right? So the way we measure time is a human invention. Now that we talked about time and time being part of nature itself, let's try to describe time in the way we measure it. Okay, so how do we measure time?
We have, as a race, devised a way to measure it in terms of the sun. So we have hours, seconds, minutes, but it's all based off of the sun's position in the sky.
Okay, so I'm going to give you 5 points. Einstein is the guy who came up with the best definition of time. He said time is what's measured by a clock. That's it. That takes a genius. Time is what's measured by a clock. So we don't have to philosophize about it. Time is what's measured by a clock. Beautiful, to the point. We're done with it. Got it? So that's what time is. So time is what's measured by a clock. Okay, guys, pick out the best answer. Whenever you're ready, all right, just tell me what it is. Okay, which B is the best answer? So who said B? Those of you guys who said B, give yourselves 5 points. Those of you guys who picked B, give yourselves 2. That's nice, guys. So B is exact definition of it, right? This time is what's measured by a clock. A is not the correct answer because it talks about where the concept of time originates from. So we don't care about where the concept comes from. The only thing we have to worry about is the way we actually express time in the way we measure it. So the time is by a clock. So that's awesome. The next one is space. All right, so what's space? All right, jump in. Whatever the idea you may have, we'll just, okay, somebody said it's a vacuum. That's fine. I'll give you 2 points for that one. Everything around us, that's also fine. I'll give you 2 points for that one. So try to describe space in the way we measure it. All right, guys, how do we measure space?
We, as distance, usually.
Yeah.
Okay, the distance, I'm going to give you 5 points for it. All right, anyone who said distance, give yourselves 5 points for that one. That's beautiful. You measure it in terms of this. Is if it's one-dimensional, obviously you measure the length. If it's two-dimensional, you got this length and that length, so you get the area. If it's three-dimensional, obviously you got the length, you got the width, and then you have the height, so it becomes three-dimensional. That's it. Once again, the best definition comes from Einstein. Einstein will say what's measured by a measuring stick. Yeah, so you can measure a single dimension, 2 dimensions, and 3 dimensions. So you end up getting a length, area, the volume, whatever. All right, so space is what's measured by a measuring stick, yardstick, meter stick. All right, so time is what's measured by a clock. The space is what's measured by a measuring stick. All right, the next one is, let's talk about mass. How would you define mass? What do you think that the best definition of mass is going to be? So time is what's measured by a clock. Space is what's measured by a measuring stick. So which means that the mass is
How much matter weighs?
I see density. Those of you guys who say anything, give yourself 2 points. Somebody says property of an object, give yourself 2 points. I see weight, and some of you guys said weight. Those of you guys who said that, give yourselves 2 points. All right. So you guys are thinking, I mean, how do you measure your weight? So you guys are thinking that mass is what's measured by a scale, right? That's the way you guys are thinking. I mean, if time is what's measured by a clock, if space is what's measured by a measuring stick, and you're thinking that the mass is what's measured by a scale, and the answer to that question is no. The mass doesn't have much to do with weight, believe it or not. Weight is the gravitational force acting on a mass. You may be weightless, but you will still have mass. So the question is, what is mass? Okay, so somebody, Lance said that your mass changed on the moon, but your weight will give yourself high points. That's also correct. All right, so what is mass if that's the case? Guys, the definition of mass is an old one. Right? It goes all the way back to Newton. The definition is 350 years old. All right, just don't copy it down immediately. Just let's play with the concept. It's a measure of inertia. All right, Newton is the guy who came up with that. Inertia means the tendency of an object to retain its initial motion. All right, so inertia is related to the tendency of an object to retain its initial motion. And what's meant by motion is velocity. And the velocity in this case is a combination of speed and direction. Okay, so it's a really weird philosophical definition that you have. All right, so now instead of just wrestling with it as this, let's play this game, and then I'm going to give you a really simple way of looking at it. So mass is a measure of inertia. All right, so it's the measure of the amount of inertia that the object has, or otherwise known as measure of inertia. So inertia is the tendency to retain initial motion. All right, motion is velocity, and velocity is a combination of speed and direction. Now, when you guys are studying, this is what you guys do. You normally would memorize stuff without understanding it. And then more you repeat it, more it makes sense, but you never get a full understanding of it, unless somehow you're able to relate it to something from real life. Okay, so let's do that. Let's relate it to something from real life. All right, what does it feel like to be hit by a fly right in the face at 60 miles per hour?
Annoying.
Yeah, that's it. Slight pinch on the face, and you go, oh, gee, I think I just got hit by a fly. So what happens to you? Nothing. What happens to the fly? Dead upon impact. That's it. So what would it feel like to get hit by a train at 60 miles per hour?
It hurt a lot if you lived long enough.
All right, Jack, I'm gonna give you 5 points. The impact lasts a fraction of a second. All right, impact time is normally so small that you wouldn't even feel a thing. All right, that would be a permanent out-of-body experience. All right, without any pain. Getting hit by a train is not gonna feel like anything. Getting hit by a fly, you will feel it. That's the weird thing. A fly, you will feel. A train, you won't. So what's the difference between getting hit by a fly and getting hit by a train? All right, fly comes to a stop. How about the train? It's got
The amount of surface area impacted.
All right, give yourself 2 points. So what's the difference between getting hit by a train and getting hit by a fly? Fly will come to a stop. Train is going to keep on moving, right? Why is it that the fly comes to a stop and the train does not? Because, very good, because the train is much more massive. Train has a much larger tendency to retain that initial motion. Got it? So if you could measure that tendency, it's known as mass. All right, so where do you get that tendency from? You get that tendency from your mass. All right, so now let's get back to the definition one more time. What's mass? It's a measure of inertia. So Newton came up with the concept. Inertia is the tendency to retain initial motion. So the motion is the same as velocity. So you have a tendency to move in a straight line at a constant speed. And that tendency comes from your mass. That's what it means. So if you can measure that tendency, that becomes your mass. So measure of that tendency is your mass. All right, I'm looking at some of the comments on the side. Fly smarter than the train. Every time you do a comment, give yourself 2 points for that one. Right or wrong, it just, I want you guys to be as engaged as possible with this. All right, so open this up. Hopefully you guys are taking notes. Okay, so what's motion? All right, so jump in at this point. So we are doing a fast review. So
of mass and time and space.
Okay, give yourself 2 points. So every time you answer a question, give yourself 2 points. So what's motion? Is the displacement of mass in time and in space. Very good. So if that's the case, what are the only measurable quantities in describing motion?
Mass times space.
Mass.
Okay, very good. Mass times space. Very good. Give yourself 2 points for that. How's time defined in physics?
What's measured by a clock?
What's measured by a clock? Okay, question number 4, we will skip it. We'll get back to the short thing. How's mass defined in physics?
What's measured by measuring stick?
What's measured by a measuring stick? Okay, question number 6, skip. Question number 7. How's mass defined in physics?
The inertia.
Okay, very good. That's the measure of inertia. All right, measure of inertia. So inertia, obviously, just put down like train versus a fly hitting a person, and your mind will go to the concept immediately. All right, so far so good. All right, so at this point, we will have to take notes. So I'm gonna switch back. All right, so current lecture is gonna be on motion. So our topic is motion. All right, so in terms of motion, motion is how fast an object moves in space and in time. All right, so here's your object. You got mass. So what's going to happen is this object is going to get displaced in space as well as in time. So this thing is going to traverse a certain distance along the x direction, and it's going to take time for it to move this distance. All right, so you got the mass getting displaced in space and in time. All right, so m is going to be our mass. X is going to be our space, so it's one-dimensional, so this is going to be our distance. And t is the time it's going to take for us to traverse this distance. All right. Time is going to be measured in terms of seconds. Distance or space is going to be measured in terms of meters. And the mass is going to be expressed in terms of kilograms. All right, so kg, this means kilograms. M means meters. S means seconds. Okay, so these are the proper units that we will get to use. All right, so we end up using the Extended International System for describing motion, otherwise known as the MKS unit system. All right, so this is known as the MKS unit system. Okay, so where M stands for meters, K stands for kilograms, and S stands for seconds. All right, so we got meters, kilograms, and seconds, so that's our standard international unit system. All right, so the next topic that we will focus on is distance versus displacement. So what's distance and what's displacement? Let's just focus on that one. So we will have a subtopic. And let's talk about distance versus displacement. All right, in the way we use these concepts in English, they seem like they mean the same thing. Let's just compare this. All right, so distance versus displacement. All right, so what's distance and what's displacement? All right, distance is the total path traveled. All right, so this represents the total path traveled. All right, displacement is a little bit different. Displacement is the shortest distance between 2 points. Where the position is denoted by an arrow. So what you have is its final position is going to be denoted by an arrow, which means that it's going to have a direction. That's what it means. All right, so distance versus displacement. Distance is the total path traveled. Displacement is the shortest distance between 2 points, and the position, the final position, is going to be denoted as an arrow. Okay, so how does that go? All right, imagine that you're rich. All right, so we're making stuff up right now. Rich enough to have a boat, and then you're going to Lake Michigan over the weekend. And on Sunday, you get your friends and you guys get your beer, and then you do a little bit of traveling. All right, so this is the coastline. And then here's what you do. You guys start off at this point and then meander around, and then you're on the way back, and then boom, engine breaks down. All right, so now you need help. You call up the Coast Guard, and what information do they need from you? All right, you know that you've been traveling roughly about 100 miles. All right, is this information relevant to your rescue? The fact that you've been traveling 100 miles, yes or no?
No.
That information is not relevant. So the total distance you traveled, it doesn't mean anything to anyone. So what information would they want if they can get it? The information they want is your location, right? They want your location on a coordinate system, on a map, all right? So they want to know exactly where you are relative to them, in essence. So notice that you got 1 point here. This is where the Coast Guard is. And here's a second point. This is where you are, all right? So that they want the shortest distance between you and them, and which is going to be indicated as an arrow. Okay, now this arrow is known as displacement. This is your displacement. As this so happens, this is about 30 miles. And this is going to be northeast, easterly direction that you're looking at. All right, displacement is known as a position vector. All right, so it's got a name. It's also known as a position vector in this case. So displacement, it's got a name. It's known as the position vector. So it locates you on a coordinate system in a sense. Okay, now we got a problem. The problem is we talked about distance, we talked about displacement, and then we end up using a weird term. We got the displacement, and we also said that's a vector. It's a position vector. Okay, so which means that we need to have one more discussion. Okay, so what is a vector? All right, so what's a vector? And speaking of vectors, what is a scalar? All right, scalar and a vector. So those are the two terms that we need to discuss real fast. Scalar, if you hear scalar, scalar is just a numeric expression. It's going to give you magnitude. All right, scalar, anything with magnitude alone is known as scalar. So magnitude means it's just a number, guys. Anything that has a size is a scalar. All right, so let's come up with some examples of things that could be scalars. All right, so time is a scalar. It's just a number. Okay, what else? Pressure is a scalar. All right, so it's a number. What else? Your weight is a scalar. All right, anything that has magnitude is known as a scalar. Your speed is a scalar. That tells you how fast you're moving. All right, what else? The temperature is a scalar. All right, those are known as scalars. Anything that has magnitude, anything that has size, anything that has value is a scalar. Now, vector is a combination of a scalar. So it's a magnitude with direction. So it has direction. Anything that has magnitude and direction, anything which is a combination of magnitude and direction is known as a vector. Case in point. You can push objects in the forward direction or you can pull them in the backward direction, right? So which means that the force is a vector. Push is a force, so force is a vector. Force is direction. You can speed up in a given direction and you can slow down in the opposite direction, right? So which means that the acceleration is a vector. You could be moving at a constant speed, but you could also be moving at a constant speed in a given direction, so which is known as velocity, which happens to be a vector. All right, so anything that has direction is known as a vector. So force is a vector, velocity is a vector, acceleration is a vector. All right, so those are, all right, so let's get rid of this one. So those are three examples of vectors. Okay, so what's motion? It's how fast an object moves in space and in time, so we got that. Measurable quantities, it's gonna be time, space, and mass. Time is defined in terms of what's measured by clock. So question number 4, so what's the proper unit for mass? No, what's the proper unit for time? So the proper unit for time is
Seconds.
seconds. Give yourself 2 points for that one. And what else? All right, so question number 6. 5 is how space defined, so that's what's measured by measuring stick. What's the proper unit for measuring distance? In
Meters.
physics? It's gonna be meters. Give yourself 2 points. Mass is the measure of inertia. What's the proper unit?
Kilograms.
Kilograms, very good. What does MKS stand for?
Meters, kilograms,
Meters,
seconds.
kilograms, and seconds.
Okay, very good. Give yourself 2 points. All right, what's distance?
Total paths traveled.
Very good. So it's a scalar. Okay. What's the displacement?
Shortest distance between where the final position is.
Okay, very good. It's a position locator, right? It's the shortest distance. So what that means is it's also a vector, right? Displacement is the shortest distance between 2 points, with the final location is indicated as an arrow with respect to the initial position. Okay, very good. So it's 7:19. Take a break for 10, and then we will continue. All right, so we talked about distance versus displacement. So what's distance? Distance is the total path traveled. Displacement is the shortest distance between 2 points. It's a position vector. All right, so me traveling all the way to San Diego. I meander around, so that's the total path. And this is the displacement that you're looking at. So that's the shortest distance between 2 points. An arrow indicating the location with respect to the initial point. All right, so distance is a scalar. Displacement is a vector. So we got a scalar, we got a vector, so that's what we do. So a scalar is just a number, anything with a magnitude. Examples, you got time, you got distance, and you got speed. Vector is a quantity with direction. It's a combination of a number and its direction. So velocity is an example, acceleration and force, and that's it. All right, so now let's talk about speed. What's speed? Speed is how fast an object moves in space and in time. Okay, Lance, give yourself the points. It's how fast an object moves in space and in time. It's going to be directly proportional to distance, and it's going to be inversely proportional to time. topic. All right, so we'll talk about speed. All right, so speed is how fast an object moves in space and in time. All right, so here's the mass. It's going to get displaced in space as well as in time. And it's going to have speed. All right, so distance over time is our speed. All right, so x is your distance. T is your time. And v is the speed. All right, so distance is here measured in terms of meters, time in seconds. And what that means is this one is meters, and this one is in terms of seconds. So speed is going to be in terms of meters per second. So this will be meters per seconds. Okay, so that becomes the proper unit. So speed is how fast an object moves in time and in space. All right, so the proper unit is going to be meters per second. In the United States, we use miles per hour. Here's the conversion factor. All right, so 1 meter per second is going to be 2.24 miles per hour. And here's the formula. Okay, so you will find the formulas and the conversions on the formula sheet. All right, so open up the formula sheet. Looks like that. Formula that we were just discussing, talking about is located here. And just go to the very last page. And then you got the conversions here. 1 meter per second is the same as 2.24 miles per hour in terms of speed. So that's what we will get to use. In terms of distance, R is going to be our distance. Meter can be expressed in terms of feet, and mile could be expressed in terms of meters. Okay, so the stuff that we will need, those are the ones we will focus on. Also, I want you to know time. 1 hour is going to be 3,600 seconds. What else do we need for now? That's pretty much it. All right, so understand the distance, understand the speed, understand time. So those are the ones we will use. And the formula that we're focusing on is located here. All right, so that's our formula. All right, so okay, so in terms of the MKS unit system, what's velocity measured in?
C.
All right, those of you guys who said C, give yourselves 5 points. Those of you guys who pick C, give yourselves 2 points. All right, C is the best answer. All right.
This is the fastest man on the planet. Michael Johnson, the world and Olympic 200 and 400 meter champion. The 1996 Atlanta Olympics 200 meter final. Johnson prepares himself for the race of his life.
As I'm in the blocks, the only thing I can be thinking about at that moment is reacting to the gun. You know, I can't think about what I'm going to do, you know, even 10 meters into the race or even 2 seconds into the race. I can't be thinking about that at that point because there's something more important. I've got to react to the gun, and you have to take the race phase by phase and focus on each particular thing as you get to it.
Johnson smashed the world record with a time of 19.32 seconds.
Very confident.
At 26, Greene has reason to be. His world record is 9.79 seconds. He's run 100 under 10 seconds more than any man before him.
All right, so who is faster? Is it Johnson who ran 200 meters within 19.32 seconds, or is it Maurice Greene who ran 100 meters within 9.79 seconds? Okay, so that's what we're gonna try to figure out. Okay, so notice that we got problems here, which is kind of neat. All right, so that's the problem that we will get to do. I'm just gonna copy this, just pull it out. And then I want you to go into the worksheet because the worksheet is the one that we will get to use. Okay, your worksheet is going to look a little bit different from that, but you can format it to look like this. Okay, so what I'm going to do is I'm going to get yours to look like this at some point. Okay, so let me just pull this up. I'm going to put the problem here so you guys can see how I'm going to solve this problem. Okay, So one of the things that I'm going to do is just look at the numbers. You got 200 meters, you got 19.32 seconds, and I'm interested in the speed. Okay, so obviously 200 meters is going to be our x, 19.32 seconds is going to be our t, and speed is going to be our v. Okay, so the first thing I have to do is just list everything. So that's what I'm going to do. All right, so x is going to be my 200 meters, and t is going to be 19.32 seconds. And speed is what I'm looking for, question mark. And we will get the answer in terms of meters per second. That's it. So everything is formatted. All right. So once again, 200 meters, he's running 200 meters. So that's x. 19.32 seconds, that's your t. And we want to know what the speed is right here. So we want the speed in terms of meters per second. Okay, so I listed everything. So we're done with step number 1. The next step is going to be algebra. Okay, so algebra simply means just find the right formula and use it. Now, picking up the formulas are easy. The only thing you have to do is just look at what's given and what's being asked for. So find the formula that has x in it, t in it, and v in it. All right, and then obviously in this case, we have only one single formula, which is distance over time is going to give you your speed. That's it. Notice that the unknown is on the left-hand side, and we are looking for v, so the v is also here, so we're good. All right, so this is the formula. No algebra is needed. We just pick the right formula, and we're done. Next step is the numbers. It says numerical here, so which means that just use the numbers. Plug the numbers in. All right, so v in this case is what we're looking for. All right, so x is 200, just use 200, and t is 19.32. All right, don't worry about the units, just use the numbers. All right, so we got 200 divided by 19.32. That's it. Okay, at this point, you will have to use a calculator. All right, so I'm gonna actually rely on you for the numbers. Okay, so just get a calculator or get on the internet and run your numbers. Okay, Lynn, those of you guys who did it, yeah, those of you guys who did it, give yourself 5 points. That's nice. So 10.35 is what I see in the chat, so that's actually correct. Okay, very good. All right, so this is how fast Johnson was running, so we were good with this. Okay, so now what we need to do is, okay, so we're done with this one. Speed is done. Very good. Now it says here that now you got to convert it to miles per hour. All right, so and then we have to show what. So convert it to miles per hour. So which means that we have to multiply this with the conversion factor. All right, so conversion factor, and we know what the conversion factor is. I'm just gonna get out of here. Just go to the formula sheet. All right, and know where to find it. So I'm just gonna cheat at this point. So whatever the conversion factors I need, I'm just gonna grab them. All right. All right, so the conversion factor is going to be meters per second to miles per hour. 1 meter per second is the same as 2.24 miles per hour. Like units will cancel. So what that means is you have to multiply this by that number. And when you multiply those two numbers, what do you get? You end up getting, what is it, 23.18. Okay, very good. I see. Those are, some of you guys already have done it. So give yourselves 5 points for that one. So miles per hour. All right, so roughly about 23 miles per hour, a little bit over 23. All right, so what do we know? Johnson was running a little bit over 23 miles per hour, so that's what we got. All right, so speed of Johnson was a little bit over 23 miles per hour. So let me just denote this, let's say this is Johnson. All right, so we got a speed for Johnson. Okay, so I'm happy. All right, so I got Maurice Greene. Okay, so what do we know about Greene? Once again, we know the distance, that's x. We know the time, that's t, and then figure out the speed, which is v. Okay, so just transfer the numbers. So x in this case is 100 meters. Time is 9.79 seconds. And the speed is a question mark. Proper unit is meters per second. And then we want the speed in terms of miles per hour at the end. Okay, step number 1 is complete. Okay, so we listed everything. There are no conversions, so all right, so got the metric unit system, MKS unit system, so meters in seconds, meters per second, so we're good. All right, so we got a formula for speed, so that's what we need. Again, algebra is straightforward. Distance over time is our speed. And the next step is just plug the numbers in terms of the metric units. X is 100, T is 9.79, and that's it. So 100 divided by 9.79. Okay, so what do we have? A bunch of you guys are done with that. Give yourselves 5 points. So that's going to be 10.21. So we end up getting 10.21 meters per second. Okay, once again, I'm going to show work for a while, and I'm going to expect you guys to show work as well on the test for a few weeks. Once you get the hang of it, it'll be good to go. So meters per second to miles per hour. So what do we have? 1 meter per second is 2.24 miles per hour. So which means that the answer is going to be 22.88. Very good. I see a lot of 88s. Give yourself 5 points. Miles per hour. Okay, I think we kind of have our answer at this point. Okay. So what do we know? We got Johnson right here, over 23 miles per hour. And then we got Greene here, under 23 miles per hour. So we got Greene. All right, so Maurice Greene. Okay, so who's faster? Is it Johnson or is it Greene?
Johnson.
Okay, immediately you say Johnson, right? Why did you say Johnson is faster?
Because he's traveling a farther distance over time than Greene is.
All right, I'll give you 2 points for that one. All right, guys, who's faster? Is it Johnson or is it Greene? And why? I need an explanation. Okay, so this is what people debated for almost 10 years. So what's there to debate? That's what I'm getting at. Who's faster? Is it Johnson or is it Greene?
Johnson.
Okay, so why did you say Johnson is faster?
Because he travels more distance in an hour because he travels 23.18 miles per hour compared to Greene. So he travels more distance in a shorter amount of time, or in the same amount of time than him.
So that makes him faster?
Yeah.
Oh, okay. I'm going to give you 5 points for that one. Okay, now watch the confusion, guys. Who's faster? Look at the numbers.
The same, the same.
Okay, who's faster is meaning who's moving at a higher rate, right? So 23.18 is larger than 22.88, right? This is more than 23. This is less than 23. That means that Johnson has to do faster than Greene, right? Okay, simple enough. All right, now watch the confusion. We will just debate this and see what happens. All right, if Johnson is faster, guys, how come Greene is the one who has the world record for 100 meters? Johnson had the world record. Johnson had the world record for 200 meters. Greene had the world record for 100 meters. Okay, so how's that even possible? If Johnson is faster, he was also supposed to have the world record for 100 meters. If Greene is faster, he's also supposed to have the world record for 200 meters. What the hell is going on, people? Why is physics so complicated? We got our numbers while we're still stuck. So what do you guys think?
I think it's
acceleration.
Okay, so acceleration means someone is quicker. Does this mean that person is faster?
I mean, maybe he sped up. He sped up as like Johnson could have sped up even faster as towards the end of the path or the race. I don't know.
Okay, so I'm gonna give you 5 points for that one. Who's faster if that's the case? Is it Johnson or is it Greene? I mean, Greene had the world record for 100 meters. Johnson had it for 200 meters. So what does it mean? Who's faster? The only thing I want you to notice is it's very easy to confuse yourselves if you're not careful. Okay, I'm looking at the numbers. Obviously, Johnson has a bigger number, so that means that the Johnson has to be faster. And immediately somebody's going to say, wait a minute. If that's the case, Johnson is also supposed to have the record for 100 meters, and yet he doesn't have the world record for that. If Greene is faster, you can also make the argument that Greene would have the 200-meter record. So it just doesn't make sense. And all of a sudden people go, wait a minute, Greene is probably faster because he has a 100-meter record, right? Do you see the confusion, how fast things get confused when you actually allow yourself to get confused? So let's settle that debate. Let's get back to the reason why everything got so confusing. The reason why everything got so confusing is because of NBC Nightly News. All right, referring to Maurice Greene, they said his top speed was 27
miles an hour, as fast as an eagle flies. His shoes, size 10.5, a new design for greater power. Covered, no surprise, with stars of gold, putting Greene on a very fast track to Olympic gold.
All right, let's get back to this one more time. Oh, didn't need to get out of it. All right, it's supposed to show this. Okay, let's get back to it. All right, I want you to notice a couple of things about commercial TV.
Speed.
Number one, they are talking about Maurice Greene. They say at some point it was going at 27 miles per hour.
27 miles an hour.
All right, so now who's faster? Is it Johnson at 23 miles per hour? Is it Maurice Greene at 27 miles per hour? All of a sudden you go, wait a minute, now 27 is bigger than 23, so that makes him faster, right? So which means that Maurice Greene has to be faster. And then immediately you start to see problems. Okay, a couple of things that I'm seeing here, and all of a sudden I go, wait a minute, this looks a little bit made up. Each step, 1/10 of a second on the ground. How would they know? Why would they care? 400 pounds of force, where'd they get that from? And top speed 27 miles per hour, how would they know that? Okay. And then the weirdest
Fast as
thing,
an eagle flies.
they say the Eagles fly at 27 miles per hour. I wonder if they saw an eagle matching speeds with Maurice Greene. Is that how they came up with that? Because eagles don't fly at 27, guys. It's like 120 miles per hour. So that stuff is made up. And then it gets weirder. Guys, this is nightly news, all right? This is nightly news. This is something that you're supposed to be able to trust when you're watching TV, all right? This is not Fox. This is not made up news. This is NBC, all right? They have reputation.
His shoes size.
And all of a sudden, there's this focus on the shoes. All right, so they're focusing on the shoes. So
Covered, no surprise, with stars of gold.
all right, this being commercial TV, what do you think you're going to see right after this news item?
Shoes.
It's going to be shoes. They just primed it for it, guys. It's not going to be a Coke commercial. It's not going to be a Pepsi commercial. It's going to be a shoe commercial, and they're going to try to sell you shoes at this point.
Putting Greene on a very fast track.
So what they're saying is it wasn't Greene that was running that fast. It happened to be in the right shoes that could run at 27 miles per hour.
The gold stars.
This is like the dumbest thing ever. All right, 27 miles per hour. All right, what's he going at 27 miles per hour? Because we've done the numbers, it's like under 23. And then how'd they come up with that number? All right, so we'll keep investigating. Okay, let's do a fun little problem. This is problem number 3. It's Godzilla. All right, this is a creative project done by one of the Chicago students. Okay, let me check to see how long. Oh, this is cute. All right, so
ran from the Chicago police for an hour and a half on Lakeshore Drive, and he covered 50 miles. How fast was he running? Let's go to the film. Let's watch that one more time.
all right, so this is going to be our problem number 3. We'll get back to it shortly. All right, so what do we know? Okay, we know the time. It's going to be an hour and a half. So that's going to be our T. We also know that it covers a distance, which is 50 miles, is X. And then let's figure out how fast it was moving. Okay, so the time is given. It's going to be 1.5 hours. We also know the distance. Distance is going to be 50 miles. All right, and then we need to figure out the speed. Okay, we want the speed in terms of meters per second. Okay, here's what I'm gonna do. I'm gonna format it for you. This is not the fastest way of doing it, but this way always gonna work. So let's develop some good habits. All right, the hours needs to be expressed in terms of seconds. Mile needs to be expressed in terms of meters. And the time, and of course we are fine with that one. Okay, let me get back to our conversion factors from the formula sheet. I was not able to save it for some reason last time. All right, let me check to see if it works this time. All right, so copy that. Okay, now it works. As an image, it works. All right, so we got that. What else? We will need the distance in terms of miles to meters. And remember, 1 hour is going to be 3,600 seconds. All right, so. All right, so these are the 2 conversions that we will need. This is a bit of a conversion exercise. Okay, so just remember, guys, we listed everything. Everything is listed. And then the next step is conversions to the metric units. So we have to go from hours to seconds. So 1 hour is going to be 3,600 seconds. And then we have, let me just move this down a little bit. All right, so we got a mile, and we have to express it in terms of meters. All right, so the conversion factor is here. So 1 mile is going to be 1609 meters, and that's it. Okay, so I just need the numbers in terms of seconds, and I need the numbers in terms of meters. Okay, 1.5 hours is going to be how many seconds?
Be 5,400 seconds.
Okay, 5,400 seconds. Give yourself 2 points. And 50 miles is, what is it in terms of meters?
8,000 or 80,467.
All right, so give yourself 5 points for that as well. Okay, that's it. So we did the conversions to the MKS unit system. Okay, algebra is the same as before. In this case, it's just a single formula, distance over time. And that's it. Okay, now what we need to do is we need to use the metric units.
I got something different for the meters.
What'd you get?
I got 80,450.
I got that too.
450. Okay, how many of you guys got 450? 80,450.
It is 450.
Okay, so all of you guys give yourselves 5 points. 450. All right, so this is 450 stone meters. Okay. All right, so X is this number. T is this number. All right, so plug the numbers in. X is going to be 80,450. And T is 5,400. Okay, so I see the numbers on the side, which is good. Those of you guys who came up with the numbers, give yourselves 5 points. I see 14.9, 14.88. Okay, both of them are good numbers. So let me just grab 14.88 for now. So this is what we have. And the next thing that we will have to do is just let's do a conversion. All right, so multiply with the conversion factor. So let's go from meters per second to miles per hour. So here's our conversion factor. Get rid of the like units, and I think some of you guys got them. All right, I don't see anyone. Okay, so is this like 33.33 or something? All right, so yeah, all right, cool. Give yourself 5 points, Chantel. So it's going to be 33.33 miles per hour. Once again, this is not the fastest way of doing it, but this is the best way of doing it, as you will appreciate later, because you have to do the conversions first before you dive into physics. Okay, now let's have a quick little discussion. So notice that Godzilla is running over 33 miles per hour. That's what it means. So do you think Johnson is going to be able to catch Godzilla? Yes or no? Johnson is at 23, Godzilla is at 33, so there's no way on foot you can actually catch Godzilla. That's actually a cute little example. All right, so that's not going to happen. Godzilla is still running faster than the fastest person. So that makes it impossible. All right, so this was more of an exercise of conversions. Okay, so this gave you a good idea of how you do conversions. So step number 1 is less than convert, and now we know how to do conversions. All right, so let's get back to the presentation. All right, so this is art school physics so far. I'm just trying to build up your confidence. So you guys
Godzilla ran from the Chicago police for an hour and a half.
From 90 minutes, converted to seconds.
50 miles. How fast was he running?
Okay, so pick out the best answer. All right, so best answer is, all right, so those of you guys who pick C, give yourselves 2 points. So C is the best answer for this one. All right. All right, so here's a different creative project. Let's find this creative project. And it's going through a distance of 155 miles. So how long would this take? All right, so what we're looking for is T. Speed is given, which is V, and distance is given, that's X. So let's just transfer. All right, so we got disconnected briefly. All right, let me check to see if everything is working fine. All right, so it's recording. All right. So let's move the information. So it's moving at a given speed, 800 miles per hour. And
you're freezing up.
Okay, distance is 155 miles. Okay, so I think we are fine now. And what is it that we are looking for? We are looking for the time this time. Okay, figure out the time. Okay. I just want to move things down a little bit so we can do a little bit of work. Okay, so we've got a bunch of conversions. We'll have to do a bunch of conversions and check to see if I can grab these from here. Okay, all right, that's good. Just put them to the side for future use. All right, so let's do the conversions. We got miles per hour to meters per second. So 1 meter per second is 2.24 miles per hour. I mean, you got the information right there. All right, so that's one conversion. Let me just make a little bit more room. And then we need to do a conversion between miles and meters. All right, so miles and meters conversion is there. So 1 mile is 1609 meters. Okay. All right, so let's get the numbers now. All right, let me just see that. All right, so 800 miles per hour. I see that it's 357.14 meters per second. Those of you guys who came up with it, give yourselves 5 points. All right, I see 357.14, so that's good. So that's how fast in terms of meters per second. And miles, I see 249,000 and 395 meters. Okay, so give yourself 5 points for that one. So those of you guys who came up with it. Okay, that's pretty good. So most of you guys came up with it. Okay, the next thing is obviously just looking at what's given to you. The only formula that we can apply is going to be our speed formula. So you got x divided by t, and that gives you your speed. That's good. Except here's the problem. The problem is we want to solve this for t. All right, so when we start out with the formula, now what we need to do is we need to find t. All right, no numbers at this point. I want to see the algebra in the symbolic form. So what do we do? We have to switch these two. All right, so we have to switch those two. Okay. All right, so those two will need to switch places. All right, so t goes to the left, and v goes down to the denominator. And here's the final format. So we end up doing a one single step algebra. Okay, so this problem was straightforward. Now we did our algebra, that's it. All right, so the next step is the numbers. It's a numbers game at this point. Okay, so speaking of numbers, obviously we have to use the metric units for x. And for speed, okay, I made a mistake. All right, so x is located right here. And v is located right there, so this is the number we use for it. Okay, so x is 249,395, and v is going to be 357.14. Okay, so I'm looking at what you guys came up with, and most of you guys are one step ahead of me, which is good. I'm noticing that just about every single person came up with the same number. So in terms of time, we end up getting this almost 700 seconds. All right, so almost 700 seconds. So I'm just going to wiggle this. Okay, here's your wiggle. All right, so wiggle is going to be an approximation, and that's 700 seconds. All right, you end up getting 700 seconds. So if you're traveling 800 miles per hour, it's going to take you about 700 seconds to travel a distance of 155 miles. All right, so within 700 seconds, you travel this distance. Okay, except here's the catch, guys. The stuff that doesn't make sense. Expressing time in terms of seconds, perfect in terms of physics. All right, this satisfies physics, but this doesn't satisfy real life. Case in point, if you're late to an appointment, all right, if your boyfriend, girlfriend is waiting for you, if your friends are waiting for you, if your family is waiting for you, you would never say, guys, hold on, I'm going to be there within the next 700 seconds. All right, just try to talk to people like that, check to see what happens, guys. Somebody's going to dump your ass. Your parents are going to try to disown you. You're going to end up losing your parents. You're going to end up losing your friends. You can't talk like that in real life. You know, what makes sense in physics makes no sense to other people. It's like the Big Bang Theory, Sheldon, okay? That's the way he speaks. 700 seconds doesn't mean anything. So what do we have to do? We've got to convert it to something that makes sense to us, right? So my recommendation is obviously you got to take this and then convert it to minutes, and let's just check to see if that makes sense. All right, so go from seconds to minutes. If the number is still bizarre, okay, so remember this is what's getting converted here. Okay, so I don't have it in the formula sheet. I kind of expect you to know that 1 minute is 60 seconds. If you don't know it, just Google it just to make sure. All right, and so seconds will be expressed in terms of meters, and then what do you get? When you convert it to that, you should get, what is it, 11.6 minutes. Very good. I see the numbers on the side. It's going to be 11.6 minutes. Perfect. Or roughly about 12 minutes. That's what you should get. So it will literally take you about 12 minutes to travel 155 miles at that speed, at 800 miles per hour. So T, I'm gonna, once again, wiggle it, I'm gonna make it 12 minutes. Okay, now this was a good exercise of formatting. Okay, this had everything in it. You had to do the listing, so this is good. You had to do the conversions, so that's also good. And we end up doing a little bit of algebra, so algebra was good. And the numerics stuff, we are showing a lot of work here. You don't have to show this much work normally, but I just want you to see how the concepts develop. You know, this is what you get, but this is what you report out. This is roughly about 700 seconds, and then this doesn't make sense. So you say, okay, it's about 12 minutes for communication purposes. Okay, guys, take a break for 10. Be back by, what is it, 8:35. Oh, I love this one. The reason why I love this one is because I love the title of it, Dating a Cycle. So how many of you guys are dating a cycle currently, or how many of you guys have dated a cycle before? Evidently, exclusively, that's what I used to date. Cycle is a person who makes unreasonable demands on your life, on your time. All right, so imagine that you're dating this person. And so you're in Schaumburg and she's in Chicago. She calls you up. She says, I want you to be here within the next 20 minutes or else. Now that's a cycle. All right. And for whatever reason, you value the relationship because you don't know any better. And so you're trying to actually get to Chicago within 20 minutes from Schaumburg. So the distance between the cities is about 32 miles. So the question is, how fast do you have to go in order to get there to rescue the relationship? I got news for you guys. It's not worth rescuing. But if you want to attempt, make an attempt, let's check to see how fast you have to go. Some people like fireworks, and dating a cycle is a firework, guys. It's not going to last that long, and enjoy it while the relationship lasts. All right, so that's what we're going to be focusing on, relationship advice. All right, so this is our example problem. Okay, so let's pick up the speed with this one. So what do we have? So we got, she says 20 minutes or else. So you're in Schaumburg, she's in Chicago. Distance is 32 miles. So how fast do you have to go in order to rescue the relationship? Okay, cool. That's it.
Shouldn't it be 20 minutes up for T?
It should be absolutely 20 minutes. Give yourself 5 points for saying that, on noticing it. Okay, cool. So a bunch of conversions. So let's do the conversions real fast. So we'll go from minutes to seconds. And we got the second conversion here. So let's go from miles to, what is it, meters? All right, so let me grab my conversion factors from here. Okay. Bring them over here. Okay, so I got my space there. All right. So 20 minutes to, okay, so 1 minute is going to 60 seconds. 1 mile is 1609 meters. So we'll get rid of the like terms. This one is 1200, right? Okay, so 32 miles in terms of meters. What you guys got? All right, so I got more messages here. All right, cool. And those of you guys who came up with the numbers, give yourselves 5 points. 51,488 is what most of you guys came up with. All of you guys came up with, so that's good. All right, that's it. Okay, so V is what we were looking for. So speed is distance over time. Okay, now the numbers. Our X is here, T is there. All right, so let's do the numbers. So it's 51,488 divided by 1200. Okay, so this should give us a number. I'm checking the numbers. So I see, okay, there's a bit of a discrepancy. I see 42.91, which is good. I think, Lance, you may be a little bit dyslexic. Is it 42.9? I see 42.9.
42.9.
Okay, very good. 42.9 meters per second. That's very good. All right, guys, the conversion is obvious. So let's do one more. Let's do the conversion one more time. until this becomes second nature, and then we don't have to show work. Our meters per second, miles per hour. Like units will go. All right, so I'm looking at the numbers. I see roughly, is it 91, 96? Okay, 96.1911. Okay, most of you guys are leaning towards 96.11 miles per hour. So I'm gonna take that one. All right, so every single person who came up with a number around 96. All right, so he yours has 5 points, so that's good work. Miles per hour. So, all right, let's stop at this point. So roughly that's 96 miles per hour, right? Okay. Now this is called a case study. I'm trying to make this as realistic as possible. So you're in a relationship and the psycho that you're dating, he or she, says 20 minutes or else. And then you say, okay, well, I value the person or the relationship, or you don't want to be lonely. I don't know what the situation is. And you make an attempt and you sit down and you do the calculation and you say, oh, it's 96 miles per hour. So how does that work? All right, guys, if you're in a parking lot, obviously you have to, for you to be able to get to Chicago within 20 minutes, you have to get up to 26 miles per hour as you're leaving the parking lot. Sharp left and right turn, then what happens? All right, so there's going to be a rollover. So what if there's traffic? Well, just, if that's the case, I would just take the get off the road, go for the pedestrians, soft targets, and then hopefully you will get to Chicago at some point. So can you get to Chicago at 96 miles per hour? Again, news for you guys. As long as you're averaging 96, yeah, you should be able to. Right within the city, you're not going to be able to go that fast. It's kind of out of the question because you got the stop signs, the traffic lights, and you got the traffic. But once you hit the highway, you can go up to 120, 30, 48 miles per hour, right? So you can make up the difference. Now, if you're going at 140, 50 miles per hour, though, chances are you're going to end up getting a ticket, right? So you're going to get pulled over if you're going at 120 miles per hour. So that's not going to work out for you. So what you could do is, if you're in a relationship, you may be able to negotiate, okay? Or I would suggest that you negotiate. That's the best thing to do. So 96 miles per hour is not going to work. So what would be a reasonable speed for you to actually get there? What's the reasonable average speed for this to work? All right, so let's take the story up. All right, so here's the problem that we came up with. Speed is distance over time, right? But the problem with the 96 miles per hour, or Michael Johnson running at 23 miles per hour, whatever, whenever you're running, whenever you're driving, whenever you're walking, your speed keeps changing, right? Given the fact that your speed keeps changing, what does that speed represent? In this case, 96 miles per hour. In Michael Johnson's case, it's 23 miles per hour. That represents the average speed. So what's the average speed? That's the measured distance over measured time. All right, so that's going to give you your average speed. Measured distance over measured time is going to give you your average speed. All right, so speaking of dating a psycho, all right, so you try to reason with the person. You say, oh, okay, so there's no way you could go at, what is 96 miles per hour? Are you kidding? I'm like Fort Temple, couldn't even get up to that speed. If I were lucky, I was going at 70 miles per hour down the hill. All right, so you negotiate. You say, hey, honey, it's not going to work out. So I can average about 65 miles per hour. So if you're averaging about 65 miles per hour, guys, how long would it take for you to get to Chicago? Okay, so let's do it faster this time. We're going to be averaging about 65 miles per hour. And distance is still the same distance, so it's going to be 32 miles. So the question is, how long would this take? In terms of seconds, and then convert it to minutes. All right, so what I'm going to do is I'm going to cheat just a little bit because we've done a little bit of work here, so we can use this. And I want to put that right here. All right, now we got 65 miles per hour. 65 miles per hour, so converted to meters per second. 1 meter per second is 2.24 miles per hour. All right, so is it 29.02 meters per second? That gives out 5 points for that one. So it's 29.02 meters per second. Okay, cool. All right, so now we're solving for t. I think we're done with everything. Solve for t. So formula is this, x divided by t. All right, so switch these two. Now we're going to expression for t, so it's going to be x divided by v. All right, now the numbers. Okay, so x is this number, and v is this number. So we got 51,488 divided by 2902. Okay, so I'm looking at the numbers. All right, so it's going to be 1,774 seconds. Give yourself 5 points for that one. So 1,774 seconds. I see 2.2, so let's go with that one. Okay, so one more conversion. All right, so this gets converted to minutes. So go from seconds to minutes. 1 minute is going to be 60 seconds. All right, so what do we have? We got, all right, I see 29.6 seconds. Give yourself 6 seconds. Give yourself 5 points for that one. All right, so this is roughly about 30 minutes. Okay. Roughly about 30 minutes. Okay, now let's have a discussion. This is 30 minutes. Guys, at 96 miles per hour, it's going to take you 20 minutes. Now look at the numbers, it's bizarre. You're averaging 96 miles per hour. If you're averaging about 96 miles per hour, it's going to take you 20 minutes to get to Chicago. And if you are averaging 65 miles per hour, it takes you 30 minutes. Okay, what's the difference? What's the difference? You're saving 10 minutes. You're saving 10 minutes. All right, at 96 miles per hour, you're driving at crazy, crazy speeds in order to actually make up time. And you're saving about 10 minutes, guys. It's not worth it. For these, like 30 miles per hour, 30 miles to 40 miles to 50 miles, driving at crazy speeds, you're not making up that much time. If you're going at that speed, and all of a sudden you're going at 120 miles per hour, when you get pulled over by a police officer, they know you're going at 120 miles per hour, not because they know the distance that you're traveling, not because they know how long it's going to take for you to travel that distance. They know how fast you're moving because they have an instrument that can actually measure that speed. That's known as a speedometer, but they're able to measure is called instantaneous speed. So what is the instantaneous speed? Instantaneous speed is your measured speed. Your average speed is calculated speed. That's measured distance over measured time. And this is your instantaneous speed. So that's your measured speed. All right, it's a bit of a creative project based on the story that I gave you. That's dating a cycle. So she says 20 minutes or else. All right, so you do the calculations, it's about 96 miles per hour. And for you to be able to average 96 miles per hour, you have to be driving at crazy speeds. I love the acceleration. The body moves in the opposite direction. Gets pulled over and then ends up getting a ticket for it. In reality, if you're averaging 65, obviously it's going to take you 30 minutes. If you're averaging 96, it's going to take you 20 minutes. So it's not really worth the risk. That's really crazy. And Michael Johnson breaking the world record, that number that we came up with, a little bit over 23 miles per hour. What does that represent? I see a lot of C's. All right, I like the fact that you guys picked C. C is the best answer. That represents the average speed. Okay, so there are a couple of things that we need to discuss. Okay, so we got Michael Johnson, and you guys like the average speed. Okay, now let's get back to the question. Who has a larger average speed? Is it Johnson or is it Greene?
Johnson.
Johnson does, right? Okay, Johnson has a higher average speed. And which does this mean that he's faster? What do you guys think? So we kind of debated it. I said, wait a minute, if he's faster, he also would have had the world record for 100 meters, right? And if Greene is faster, then Greene would have had the world record for 200 meters as well. So why is it that the numbers kind of don't make sense? On top of that, remember NBC said that the Greene was moving at 27 miles per hour, and then I kind of made a joke out of it. But realistically, though, how did they even know that Greene was moving at 27 miles per hour? They said his top speed is 27 miles per hour. So what kind of a speed is that?
So it would have been an instant.
Very good, guys. That's the instantaneous speed, right? Where do you get the instantaneous speed from? That's the measured speed. So how do you measure speed? If you're driving, that's your speedometer, right? If you're a police officer, that's the radar gun. They knew Greene was going at 27 miles per hour at some point because they had a I'm just gonna say speedometer. I'm getting tired because they had the radar gun. So they were measuring his speed using a radar gun. This guy literally hit 27 miles per hour at some point. So all of a sudden you're looking at this guy going at 27 miles per hour. And you know that Johnson actually ran at 23. So the question is, who's faster?
We would need Johnson's instantaneous speed. We would need a radar gun on that to determine who actually ran faster in their peak.
Okay, very good. I'm going to give you 10 points for that one. Guys, you can only compare likes to likes, average speeds to average speeds, the instantaneous speeds to instantaneous speeds. All right, we have a value, top value for Greene, but we don't have that value because no one thought of, let's check to see how this guy was running when he was breaking the world record. But we can reason. All right. Greene is actually quicker. I think one of you guys made that point early on. Greene reaches his top speed sooner than Michael Johnson does. All right, he reaches his top speed within 100 meters, and that's the reason why he's able to break the 100-meter world record. Johnson, on the other hand, takes longer to reach his top speed. He's not as quick, but he's actually faster because he's got a larger average speed, which means that his top speed must still be larger than the Greene's top speed. Does that make sense to you guys? All right, so which means that Johnson has a larger average speed. That's going to make him faster. That also means that at some point he was actually moving faster. His top speed has to be larger than Greene's top speed. The only difference is Greene is quicker. He gets to his top speed faster, and Johnson's top speed is larger than Greene's. That's the reason why within 200 meters he's able to actually have a larger average speed. Okay, so this required a little bit of thinking. All right, I was gonna do some weird problem, but I'm not sure. Okay, I'm gonna skip this one. We'll probably get back to it. All right, one thing that I wanted to discuss, this average speed. Notice that none of you guys picked average velocity. All right, and there's a reason for it. I think you were looking for this, and then you found that, and we didn't discuss velocity, but in English, notice that both of them are used interchangeably. Speed and velocity kind of say they're the same. In physics, they are not the same. All right, so what's the difference between speed and velocity? Kind of alluded to it before, so let's get back to it. Velocity is a vector, so it's going to be a combination of speed and direction. This is not a multiplication sign. It should be speed and direction. I don't know why I put that. Okay, so the direction is going to matter when it comes to velocity. Now, imagine that you have two cars. One of them is going to the right, the other is going to the left. And notice that they have the same speed, but because they're not moving in the same direction, they don't have the same velocity. So we got different velocities. Velocity is a combination of speed and direction. All right, so velocity. All right, so speed is how fast something is moving. Okay, and they're positive. So this is not an addition. It's something that I came up with. It's a combination of speed and the direction of that speed. So it's a vector in essence. So it's a vector. And the vector is a combination of magnitude and the direction of that magnitude. All right, so velocity is a vector. So what if you have two objects moving at the same speed in opposite directions? What then? All right, so we may have an object moving in this direction and in the opposite direction. So this is moving at 50 miles per hour. And this is also moving at 50 miles per hour. So we got two objects moving at the same speed. Now they have the same speeds, but they're not moving in the same direction. So they don't have the same velocity. All right, so here's what we will do. If it's to the right, we'll assume that the velocity is positive. If it's moving to the left, we'll assume that its velocity is negative. So this will be a positive velocity. This is going to be negative velocity. So we'll get to use the sign notation for that. All right. Likewise, if it's moving in the upward direction, we'll say this is positive velocity. If it's moving in the downward direction, we'll say this is negative velocity. All right. So I'm going to have one more object moving in the downward direction at the same speed. So the speeds will be the same. All right. So this one is also moving at 50 miles per hour. Okay, so we got the speed in that direction. It's moving in the downward direction, so which means that we'll make this negative. Okay, now this is moving at 50 miles per hour, so is this one. So they have the same speeds. This is a negative velocity, so is this one. Does this mean that they have the same velocities? Yes or no? What do you guys think? Do you think that no, velocities are not the same? Why not? Because
they're not going in the same direction.
Okay, they're not moving in the same direction. Give yourselves 5 points, guys. They're still not moving in the same direction. So what that means is we still need to come up with more notations. All right, so we'll say this is motion along the x direction. All right, so this is our x-axis, and we'll say this is motion on the y direction. All right, so this is our y-axis. So we'll add up some notations, subscripts. All right, so we'll say this motion here is along the x direction, and this is along the y direction. All right, so we'll get to use the sign notation, as well as the plus and minus signs to denote direction. All right, so that's how we will express velocity. Okay, moving forward. What if you have an object moving in a circle at a constant speed? All right, let's draw a circle. Perfect. All right, so we have this subject in a circular trajectory. So it's moving in a circle. And let's assume that it's moving in a circle at a constant speed. Make this 35 miles per hour. So all the way around, this thing is going to go at 35 miles per hour. So here, it's still going to be 35 and still 35. So there's no change in speed. This thing is going to keep on moving at the same speed all the way around. All right. So the speed doesn't change, but how about velocity?
No, because it's going in the same orbit.
All right, so I'm going to give you 2 points for that one. All right, guys, the speed doesn't change. How about velocity?
I'm going to say yes, because if we put an XY plane in the middle of the circle, then the direction is going to be first up and to the left, and then it's going to be down to the left, and then down to the right, and then up and to the right.
Okay, I'm going to give you 10 points for that one. Guys, notice that the direction keeps changing, right? All right, so the direction keeps changing. Speed is not changing, but the direction keeps changing. All right, so velocity is a combination of speed and direction. So this thing is constant. So this one is not changing, but this thing keeps changing. If the velocity keeps changing, if the direction keeps changing, it changes the velocity. Notice that in circular motion, even if the speed remains constant, the velocity is not constant because the direction of motion keeps changing. All right, so you got two objects moving at the same speed in opposite directions. Do they have the same velocity? The answer to that question is no, because they're not moving in the same direction. In circular motion, even if the object is moving at a constant speed, because the direction keeps changing, velocity keeps changing. All right, so the lecture review materials, chapter number 2, concepts. Okay, so we covered just about everything. All right, so let's move on to this page. We did nothing here. All right, so what's speed? Speed is how fast an object moves in space and in time. All right, so it's how fast an object moves in space and in time. All right, so what's the proper unit for speed? It's going to be meters per second. What's average speed? It's measured distance over measured time. All right, so your average speed is measured distance over measured time. What's your instantaneous speed? Instantaneous speed is the measured speed. All right, so instantaneous speed is the measured speed. The average speed is the calculated speed. So what's the difference between the average and the instantaneous speeds? Average is calculated, the instantaneous is measured. Average speed requires a measured distance over measured time, and the instantaneous speed is the measured speed. So what's velocity? Velocity is a combination of speed and direction. So what's the difference between speed and velocity if that's the case? Speed is how fast, the velocity is also which direction. Speed is how fast, velocity is also the direction of that motion. 60 miles per hour is your speed, and if you're driving up north, 60 miles per hour becomes your velocity. That's what it means.